Let's talk about Algebra 2b, Lesson 4, Systems of Inequalities. To begin, we'll go over a little bit of vocabulary. So first up, a union. You guys have seen set notation before, probably starting in middle school, but let's do a refresher. So a union is a set whose only elements are all the elements that are in at least one or two or more sets. So union, you can think of the word or. For example, if we were using a deck of cards and I said, well, my first set, set 1, is the set of all spades in my deck. So the 2 of spades, 3 of spades, 4 of spades, all the way up to the king, queen, ace. And my second set is the set of all aces in the deck. Okay, what's the union of these two sets? It's kind of like, what do I get when I add them together? Well, that would be all the spades I have and all the aces. So that includes the ace of spades, which is both a spade and an ace. Okay, it includes it. But it includes cards that are spades that aren't aces and cards that are aces that are not spades. Okay, if I was going to draw a picture of a union as a Venn diagram, it could be anything. Let me switch colors. It could be anything that falls in either of these two, and that includes where they intersect, all right? That includes where they intersect, unless specified, and there's a special condition for that, which we're not going to get into. There is a special type of union where we don't talk about the overlap, but for our general purposes, it can be in both. So this would be our union, added together. Both of the properties from each of the sets, or both of the elements of each of the sets, are combined. Now let's talk about an intersection. So going back to our set example, if I once again had my set 1 being spades and my set 2 being aces, the intersection of these two says that my only elements are elements that my sets have in common. So what cards are both spades and aces? Well, that would only be the ace of spades, right? That's the only card that fits the criteria of being both an ace and a spade. So if I was going to draw poor circle, there we go. If I was going to draw the intersection of two sets as a Venn diagram, hopefully the word intersection helps you remember that it's just where they intersect. It has to be an element of both sets in order to be included in a set that is an intersection. A system of inequalities is just a system or a set of multiple inequalities. In this case, we're talking about linear inequalities with common variables. So it could be something as simple as x is less than y is less than 2. This could be a system of inequalities. There's more than one inequality, and it's an associated set of inequalities. All right, there could be 2 of these, there could be 5 inequalities in here. It doesn't matter how many statements there are, there just has to be more than one, and again, we're talking about related variables. A combined inequality or 2 inequalities in one or more variables joined with the connective and or. We'll look at some examples of that in upcoming slides. Now I want to talk a little bit more about union and intersection. So there are symbols for union and intersection. For union, it's kind of convenient. We have a U. For intersection, we have an upside down sort of U. All right? This is a symbol for union and the symbol for intersection. So if you were given these two sets, you said, okay, set A has the elements 1, 3, 5, 9, and 10. Set B has the 2, 4, 5, 6, 8, 10. What's their union? What's their intersection? First of all, just note that a set is usually denoted by these kind of curly brackets, all right, that usually denotes a set. Each item in the set, each number in the set is called an element of that set if it belongs to it. So 1 is an element of set A. This is the title of my set or the name of my set. 1 is an element of set A. 3 is an element of set A, and so on. I've got all my elements separated by commas. And all I'm saying is that I've got this group of numbers and they belong to this set called A. So you have encountered sets before. For example, you've heard of real numbers. That's a set of numbers. Whole numbers, that's a set of numbers. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, right? These are all whole numbers. They fit a certain criteria, and they are a set of numbers. So moving on, if you were asked, what's the union of set A and set B? Well, remember that's any element that is in either of the sets. It can be in one, both, or the other. So my union of my two sets would be the set. I write a new set and I say, all right, well, the A U B, or A union B, I'm just collecting all the elements from both sets. So that would be 1, and by condition, or by what's the word I'm looking for? Our standard form is to write the numbers in increasing order. So I'm going to write what I've got: 1, 2, 3, 4. I have 5 written twice. I only need to write it once. It's the same element in this case. 6, 8, 9, and 10. So you can see that I went through, I wrote the numbers from each set, and I combined them into one set. Okay, 1, 2, 3, 4, 5, 6, 8, 9, 10. So this is the union of sets A and B. If I were to pick out any element of my new set, I could find it in either A, B, or both. Now, what if I wanted to find the intersection of A and B? Remember, an intersection is where they sort of overlap. If I was going to draw an intersection with a Venn diagram, right, it would look like that. So if I wanted to draw the intersection, I would denote that like this: A with my intersection symbol, B. The intersection of A and B, well, the element 1 is in A, but it's not in B. That's not going to work. 2 is in B. It's not in A. That's not going to work. 3 is not going to work. 4 is not going to work. If you look at 5, that's in both A and B. So the element 5 is going to be in my intersection. 6 doesn't work. It's only in B. 9 is only in A. 8 is only in B. 10 appears in both sets A and B. So my set is 5 and 10. So you guys know how to do this. The only thing you're learning here is a new way of talking about it mathematically. If I had shown you those two sets of numbers and I said, which numbers do you see appearing in both lists of numbers, you would have easily identified for me, well, 5 appears in both lists, 10 appears in both lists. So what you're learning here, again, is just new mathematical language to describe this. So instead of calling this a list of numbers, we call it a set of numbers, okay? And when we say appears in both, instead we say intersection, okay? It's just a more succinct way of saying it. And instead of saying it appears in one, the other, or both, we say union. Let's look at another example. So once again, what if I want to find the union and the intersection of these two sets? And we'll take this a little quicker. So the union of two sets, and once again I'll draw our little Venn diagram. It can appear in one, both, or the other. The union of my two sets, A, U, B, is going to be 0, 1, 2, 4, 6, 8. This is the collection of all the elements in both sets A and B. What if I want to know the intersection? Once again, intersection is written, it looks like an upside down U. If I draw a Venn diagram, it's only the spots where my sets overlap, or in other words, the element appears in both sets. So the intersection of A and B, well, I don't see, so A only has one element. It has the element 1, and 1 does not appear at all in set B. So there is nothing in this set, right? Now, we can't write 0 because 0 itself is a number, right? That's actually an element. So to write 0 is not proper. What we stay in said is that the set is empty, and we denote that it looks like a 0 with a slash through it. So that's nothing. That's the symbol for saying empty. There's nothing there, not even a 0. Okay? So again, union, what we have between our two sets, sort of saying to add them together is not the correct way to say it, but kind of to combine them might be a better way to describe it. Intersection of two sets contains all the elements that appear in both sets. And if there is not an element that appears in both sets, you have an empty set like that. All right, let's look at one more example. Once again, union and intersection. So union, our symbol is U. Intersection, we've got that upside down U. One way that I think about this, to remember the symbols, first of all, union, it looks like the letter U. The symbol for union looks like the letter U. But I also picture this as kind of a container, and I think I can kind of drop all my elements into this container and it will hold them all. Okay, that's one way I think about just helping me remember which one's which. And then of course the word intersection I think kind of helps you remember that we're referring to the overlapping part of the sets. But let's get to the problem. So the union of A and B is going to be -5, -4, -3, -2, -1, 0, 1, 2, 3. So far, all I've done is just rewrite set B. So I've already accounted for 1, 2, and 3, and we've got 4 and 5. All right, so again, I've written out every element that appears in B, and then every element that I did not already write down that appears in A, and I wrote it in increasing order. What about the intersection? Where does A intersect with B? Well, I can see right away A has the numbers 1 through 5, right? So none of these negative numbers are going to work. 0 doesn't work. I do have 1, 2, and 3 in B, and I have 1, 2, 3 in A. So the intersection of these two is simply 1, 2, 3. All right, so final recap. Union is the combination of all the elements in 2 or more sets. The element can be in one set, another set, or both sets. It's included in the union set, and it's denoted by a symbol that looks a lot like an uppercase U. The intersection of sets only contains elements that appear in all of the sets listed. So in this case, an element that appears in both set A and set B. It is denoted with a symbol that looks a lot like an upside down U. All right, let's move forward. So as promised, we're going to talk a little bit about combined inequalities. It sounds more intimidating than it really is. So let's say I scored a 75% on my first math exam, and I want to earn a B in the class. So a standard B grade falls between an 80 and an 89%. And that includes 80. 80 itself is considered a B, and 89 itself is considered a B, and that's why I wrote the word inclusive, and I'll talk more about that in a moment. So what can I score on my next exam to still earn a B in the class? So this is a pretty useful skill. I've received many emails over the past or phone calls from students saying, I'm worried about my grade, what's the lowest I can get on this exam and still keep my A or keep my B, etc. So I think this is a really practical example for you guys. So we've got two things going on. Let's kind of piece this apart. So I scored a 75 on my first math exam. To earn a B in the class, my average score for my first two exams must be between an 80 and an 89. So how do we find the average of two scores? For example, if I said that I scored 100 on my next test, and I said, can you tell me what my average score is? You would know what to do, right? You'd say, yeah, take 75, add it to 100, and divide by 2. You add up the total worth of the two items and divide by the number of the items that you have. So in this case, my average is going to be 75 plus, I don't know my score, that's what I'm trying to figure out, so I'm just going to write x over 2. So this phrase represents 75, the first score for my first exam, x, the score for my second exam, divided by 2 to find the average of these two scores. Now, I'm saying it has to be, I want this average to be between an 80 and an 89. So this number must be greater than or equal to an 80 for me to get a B. And that same phrase, let me write it again, that same phrase, 75 plus x over 2, must be less than or equal to an 89 for me to get a B. So these are the two criteria I have to meet. I have to get a score, some score X on my exam, so that when I simplify this phrase, it falls between it is greater than or equal to an 80 and less than or equal to an 89. So I want to know the values for X for which this is possible. What do I need to aim for on this exam? Well, to combine these inequalities is pretty straightforward, okay? Notice that I've got this same term appearing in both. So I can just rewrite this without the and. I can say, okay, I'm aiming for something that is greater than or equal to an 80, so 75 plus x over 2, and is less than or equal to an 89. Okay, so this is my combined inequality right here. I took the word and out, and I put everything together. This statement contains the exact same information. I've just rewritten it in a more condensed way. All right, so be careful when you're doing this, just to double check again that your information makes sense. I would even maybe plug in a few test numbers to make sure you've still got what you think you have. Now the reason we're using or equal to is because this is inclusive. If I get an 80 average, I still have a B. If I get an 89 average, I still have a B. So that tells me that I'm talking about less than or equal to, greater than or equal to. All right, so from here, I'm going to simplify this inequality and try to isolate x. Now, there's more than one way to do this. You could attack one piece of this at a time. I'm going to do this all at once. So I'm going to get rid of this fraction. I'm going to multiply every piece of my inequality by 2. So just like when you have an equation and you do something to one side, you have to do it to the other. It's the same thing with inequalities. If I do it in one section of the inequality, I have to do it everywhere. So I'm going to multiply each piece by 2. 2 times 80 is 160. This is less than or equal to. The 2 cancels out. I get 75 plus x. It's less than or equal to 89 times 2. What would that be? 178. Okay. So again, I went from my word representation, I wrote it as 2 inequality statements. I combined my 2 inequality statements, and now I'm simplifying to isolate for x. All right, so my next step, I want to isolate x. I have x plus 75, so I'm going to subtract 75 from each piece of my inequality. 160 minus 75 gives me what? 85. It's less than or equal to, x is finally isolated. 178 minus 75 is 103. Now, you can't probably score above a 100 on a test, so when you're doing word problems, make sure to use proper context. So although this is the technical answer, when you submitted it, if you were doing like a multiple choice answer, for example, this would probably be the one that appears, because we know that it's standard to have a maximum score of 100% on a test, okay? And in fact, they might have even said the maximum she can score on the exam is 100, okay? That would be a constraint for this inequality. So one more time, taking the verbal or written version, we turned it into 2 inequality statements, which we combined into 1, and then using algebraic manipulation, we isolated x, and now we know that I have to score between an 85 and 100% if I want to get a B in this class. Let's keep going. So this is another type of problem you might encounter. There are tons of variations on different sort of inequality, combining inequality, set problems, all that stuff. To do an exhaustive amount of examples on them would take us all day. But I just want to give you a taste of a few different types of things that you might see. So here's something else. Average rainfall in a city called Greenville falls between 4 and 9 inches a year. Write a set that describes unusual rainfall for Greenville. So first, let's write a set that just describes their normal rainfall. I think that's going to be easier, right? So we know that their average rainfall falls between 4 and 9 inches a year. So what is a set notation that says between 4 and 9. All right, so I could write this as an inequality statement using x. So I could say x, if x is rainfall in inches, I could write this as 4 is less than x is less than 9. So my inches in rainfall is between 4 and 9. I'm using the less than, greater than symbol because they said the word between. They never said equal to, so I can't assume that. So this is just, again, the inequality representation, but they said write a set, so we know we're going to have to deal with set notation. So I'm just kind of showing you this as an extra step. If I wanted to write this in set notation, and I'm saying what is the set of numbers where our lower bound is 4 and our upper bound is 9, or the set of numbers between 4 and 9, we would just write 4, 9, right? And then we use normal parentheses since we're not including the numbers 4 and 9. So this is their usual rainfall. So it stands to reason that their unusual rainfall is any number that is not in that set. So what are the numbers not in that set? Again, since we're using a word problem, normally you would write sets starting at negative infinity. Rainfall can't be negative, right? The lowest rainfall could be in a year is 0. So I'm going to say unusual rainfall would be anything that equals 0 to 4, falls between 0 and includes 0 and 4. Or it could be our set of anything greater than 9, and I will use the infinity symbol just because it's hard to put a cap on how much rainfall there might be. I don't expect there to be infinity inches, but we'll leave it alone. So this is our usual amount of rainfall. It would fall within this set between 4 and 9. So our unusual rainfall is anything that falls outside of that set. So it would be unusual for them to receive 0 inches or up to 4 inches of rainfall, and including 4 inches of rainfall. That would be unusual. And it would be unusual for them to receive 9 inches of rainfall and anything above it. Alright, so anything outside their normal range is our set. And now I've used the union symbol to connect my two pieces because I'm saying it could be, if the number of inches falls anywhere in here or anywhere in here, that would be unusual. It would be impossible for the number of inches of rainfall per year to fall in both of these, right? That couldn't even happen. So again, I'm using a union symbol because I'm saying any value that falls in this piece, any value that falls in this piece would be unusual. So this would be my answer, this set. Let me just write it one more time so you can see it. Oops, that should be a bracket. 9 to infinity. With infinity, we always write a parenthesis because infinity never ends, so you can't really include it as a number. All right, let's press forward. What is the solution set for the inequalities x to the 5th is less than 0 or 9 times x to the 4th is greater than, and I think that cut off for you a little bit. Let's see. There we go. 9 times x to the 4th is greater than x squared. So here's another combined inequality example. Alright, so once again we've been given an inequality statement. We're trying to, all they're saying is take this and translate it into a solution set. So first of all, can we simplify anything? On this phrase, x to the 5th is less than 0, there's nothing to simplify, right? We can take the 5th root of both sides of the equation, right? The 5th root of x is x. The 5th root of 0 is 0. Any root of 0 is going to be 0. So I could do that, and I could say, all right, well, x is definitely going to be less than 0, right? So that's one piece. But really, I want to pay attention over here. I've got this 9x to the 4th is greater than x squared. How can I simplify this? Because I have no idea how to write this as it stands in set notation. I don't know how to accomplish it. But I do see that I can do some simplification. For example, I can see that I can divide both sides of my equation by x squared. On the right-hand side, this would cancel out. On the left-hand side, I would reduce x to the fourth. Simplifying, this gives me 9x squared is greater than 1. Alright, well now I can divide, let me switch colors, now I can divide both sides of my equation by 9, right? So on the left-hand side, this cancels out. Let's rewrite it again. I get x squared is greater than 1 over 9. Well, I'm not done yet, right? I still have an x squared that I have to simplify. So I'm going to take the square root of both sides. Square root of x is x. 1 over 9 becomes 1/3. For now, I'm taking positive roots. If that's something you were worrying about, for the sake of this question, I am only taking positive roots. So x is greater than 1/3. Now, as far as roots go, when you take a square root, as you guys know, there's a positive root and a negative root. If you have questions about this, just message me. For the sake of our material and what we're doing today, I don't want to spend a ton of time on that. I just want to focus on transcribing this into a solution set. Alright, so I'm going to leave it at that. Now I've got these two more simplified pieces. Right? I simplified my original statements. So now I've just got this. I've got x is less than 0 and x is greater than 1/3. One thing I will point out, I know I said I wasn't going to talk about roots that much. For those of you wondering, notice if I had taken the negative root of this, which would have been x is less than negative 1/3, notice that it's going to end up resolving and canceling out. So again, just keep that in mind. So how do I write these two statements in my box? How do I write these two statements in my box as in set notation? Well, it's much more easy now, right? So x is less than 0 would just be negative infinity to 0, right? So anywhere between negative infinity and 0, it would be less than 0. Or I've got x is greater than 1/3. So I'm using parentheses because they say greater than, and that would be 1/3 to infinity. Alright, so those are my two pieces. In my final draft, which I'm kind of writing this in a wonky direction, let's do red. My final piece would be to say negative infinity to 0, I'm just rewriting that, or, the word or would be our union, because it's allowed to be in this one or the other one, or 1/3 to infinity. So this would be my answer. So this is the solution set for the inequalities. So I took my inequalities, I reduced them, I got down to statements where I just have x is less than, greater than, less than or equal to, whatever. I just have x isolated, it doesn't have any exponent on it, and it has a relationship to some number. That is much easier to translate into my set notation. And then I took the cue from the prompt, it used the word or, and I knew I needed to use union. Had they said the word and, I would have used intersection. Now I know I said I wasn't going to talk about negative roots, but now I feel like I've teased you with it, so I will explain it briefly. Keep in mind when we take the square root of things, there's a positive root and a negative root. So for example, if I took the square root of 4, you would tell me it's 2, but it would also be negative 2, right? 2 times 2 is 4, but negative 2 times negative 2 is also 4. For the purposes of this problem, I chose not to include it, but again, notice that it would have been this piece right here. However, since we already had 0 as our constraint, we were saying less than 0. Well, if x is less than 0, x is obviously also less than negative 1/3, right? If we look at, I'm running out of space, if I look at a number line, and here's 0, negative 1/3 is over here. So again, if something is less than 0, it is obviously also going to be less than negative 1/3. Anyway, here is our solution set for this problem. Which set of ordered pairs is a partial solution set for this system? Okay, so look at this system. We've got y is less than 0 and x is less than or equal to y. It would be probably impossible to list all of the possible solution sets. And a solution set, for this, notice that it's just sets of ordered pairs. So they're saying, would -1, -1 work, where the first coordinate is your x solution and the second coordinate is your y solution. So this is a partial solution because it would be impossible to write an exhaustive list of solutions that would work for this inequality. Now, how do I know whether these partial lists are correct? Well, I would just plug in my values. So they're saying if x is -1 and y is -1, does that work? So all I'm going to do is plug it in, and I'm going to say, well, let's see. If y is -1, that would be -1 is less than 0. And x, which is -1, is less than or equal to y is -1. And then I just check whether or not both of these statements are true. So one more time, all I did was I looked at the x coordinate and it said x is -1, so I rewrote -1 in place of x. Oops, keeps doing that. Sorry, my presentation keeps switching slides on me. Likewise with y, they gave me the coordinate -1, so everywhere I saw a y, I plugged in a -1. And now all I'm going to do is check and see if these statements are true. And if the statements are true, then this is a good solution. Okay, and then I just proceed down the list. So -1 is less than 0. That's true. And -1 is less than or equal to -1. That's true. So since this is an and statement, both of those have to be true for this to be a good solution, and they were. So this first solution is good. All right. So -1, -1 works. This is the same ordered pair in all of these. Let's try this one, -6, -7. So everywhere I see an x, I'm going to plug in -6. Everywhere I see a y, I'm going to plug in -7. So I'm just going to write these as my template. Y is less than 0 and x is less than or equal to y. All right, so let's try this. So -6 gets plugged in for x, and let's use white. -7 gets plugged in for y. So is it true that -7 is less than 0? Yes. And is it true that -6 is less than or equal to -7? Well, no, right? Because on the number line, I would have -5, -6, -7, like that, right? So -6 is to the right of or is greater than -7. So this is not true. So already I can eliminate that answer, because if one of them doesn't work, then it's not a good partial solution set. They all have to be true. Let's try another one. Let's try this solution, -7, -6. So everywhere I see an x, I'm going to plug in -7. Everywhere I see a y, I'm going to plug in -6. Okay, and then I'm just going to write in the rest of my information. -6 is less than 0. That's true. -7 is less than or equal to -6. That's true. So this set works. And let's just continue on with that pair. This time x is going to be -8, so I plug in a -8 for x. Y is going to be -2. I plug in a -2 for y. -2 is less than 0. That's true. -8 is less than or equal to -2. That's also true. So that's another good solution. Let's see if this last one works out. This time x is -10 and y is -3. Y is -3. -3 is less than 0. That's true. -10 is less than or equal to -3. That's also true. So this is the correct partial solution set. All right, this one right here. It looks like somewhere in here we would have had an incorrect answer somewhere. So that's how you figure out. You have to test every single ordered pair that they give you, plug in the x and y values, as appropriate and then just solve and say, is the statement true? And pay attention to whether they're connected by an and or an or, so that you know, okay, well, does one of those statements need to be true, or do both of them need to be true? Okay, let's move forward. What is the solution set of the system of inequalities? So once again, we're just taking this and we're going to put it into set notation. So this one's already simplified. It's just x is less than 4, right? Now, this is a little bit trickier. We've got x's and y's going on, so we can't write in our normal solution set without kind of giving extra explanation. So I'm going to say it's the set of all x coordinates. We have to treat our x coordinates and our y coordinates separate. A set of all x coordinates that are in this set. X is greater than 4. So this is the set that describes x greater than 4. It falls between 4 and infinity. For y, I have to represent it again differently. It's going to be the set of all y coordinates that fall in a certain set as well. And it says y is greater than the square root of x. Okay. I can't write x as part of this set. All right? That's just not allowed. Notice that the smallest thing x can be is, 4.00000000001, right? I'm just going to use 4. So what if we plugged in 4 for x? What if I said y is greater than or equal to the square root of 4? And the reason I can get away with this is because we're using greater than symbols for both. So I'm not including this value in my set. I'm not including that value in my set. So if I simplified that, I would get y is greater than 2. All right, y is greater than 2. And how would I represent that? I would say the set 2 to infinity, where my answer is going to fall somewhere greater than 2, and at maximum it's going to be equal to infinity. The reason I was allowed to just plug in a 4 like that, again, I said, well, what's the lowest boundary of my x coordinate? And I plugged in that boundary for x in that other statement to figure out what the lowest boundary for y was going to be. Write the corresponding inequality. All right, so this time they've given us a solution set, and we're going to change it into an inequality. So we'll just look at it one piece at a time. So I've got 6, 11. All right, so I've got a parenthesis on one end, and the other end includes the 11. So for this, I would say 6, x is going to be somewhere between 6 and 11, right? Now, notice that because this is a closed bracket, it's really x is less than or equal to 11. Okay, so this is equivalent to my statement that I've just written. The set 6, 11 with a closed bracket is the same thing as saying 6 is less than x is less than or equal to 11. I've got my and symbol, my intersection symbol. And then what's my second piece? It's some number that falls within this set of 22 to infinity. So that would just be x is somewhere between 22 and infinity, so I would just write that like this, right? X is somewhere in between 22 and infinity. There were no closed brackets on this set, so I used the less than symbols. So notice that by the set notation is just more compact, right? And once you get used to it, it's almost easier to read. You know that your x is going to be somewhere in the domain or the range that they've given you. All right, so we're going to wrap up shortly, I promise. I just wanted to do a little bit of experimentation with graphing. So I'm not going to go over specific graphing problems, partially for the sake of time. What I am going to do is plug in a few systems of inequalities just so we can talk about what different things look like. Now don't worry about what I'm typing in, it's not important, it's really the image that we want to look at. So I've just typed in the inequality y is greater than 0, and you can see that it's shaded all the values for which y is greater than 0. I'm also going to plug in x is greater than 1. So now it has shaded all the regions for which x is greater than 1, and I'm going to change the color. So you can see that the overlapping region is almost sort of purple looking, right? Now I'm going to type in another equation again just to kind of create some interest. So what about 2x plus 1 is greater than y? These are equations that I'm just making up off the top of my head. They're not important, all right? Let's make that one yellow. So if I gave you this picture and you didn't know what these equations were, where they came from, but all I said to you was point to the solution, what would you do? Well, let me in fact plot a point. So notice that if I just plotted that point, it falls in a region where none of my inequalities are. A solution for a system of inequalities is going to be somewhere where all of the solutions interact or intersect, rather. So just like we were talking about set notation and intersection being where all of the elements where all the elements from each set, the common elements from each set, it's the same thing here. So I can kind of see that this like lighter orange region, oops, it's not letting me put my points where I want them. I can kind of see that that lighter orange region is going to be my solution set. So let me see if I can even kind of draw something. Let me see if it'll let me. So you can kind of see like, no, dang, it's not going to let me. Oh well. Point being, hopefully you can see my mouse moving. The point where all three of these pieces intersect is this kind of weirdly shaped region over here. So where I've got all three colors overlapping, that is my solution, all right? And if I got rid of my third line, which is C, let's see if I can delete it. The intersection of these two inequalities or equations would just be this purplish region right here. So again, wherever I have an intersection, that's going to be where my solution is. So let's type in a couple other inequalities just to kind of continue to play around to show you what some other ones might look like. Now, what if I had something like, I don't know, 3x minus 5 is less than y, and I haven't done an equal to yet. 2x minus 10 is greater than or equal to y. Let's try that. Okay, so once again, I've just put up two inequalities for you. Oops, why did it revert? All right, let's try that one more time. So again, I'm just typing in inequalities off the top of my head. It's really not important what the equations are that I'm typing in. There we go. All right, so if you looked at this graph and you were asked, you know, does this system of inequalities have a solution? Your answer would be no, and here's why. The solution region for your first inequality is shaded in blue. The solution region for your second inequality is graphed in red. There's no point where they intersect, so there is no solution for this system, all right? There is no intersection between these two inequalities. There's no solution here, all right? If you wanted to know what the union of these two inequalities were, it would just be every shaded region, period, no matter what color it is. All right, let's look at one more example. Let's do a quadratic this time. So what if we had something like that, less than or equal to y? If I can get my typing, there we go. And what about something like that? All right. So once again, just changing the colors so you can see a little bit better. Something you probably cannot see is when I type in an inequality as less than or greater than, the dark region that shows you kind of where that boundary is a dashed line. Remember, when we're talking about less than or greater than, the number itself is not included. So for example, x is less than 2. That means x is not equal to 2, so 2 would not be part of the solution set. So you, again, probably hard to see, but my red line is actually dashed because I wrote it as a less than sign. If you look at this dark blue line, you might be able to tell that it's a solid blue line, and you can kind of probably see up here, I had defined it as x squared is less than or equal to y. Alright, but anyway, so once again, if I showed you this picture and I said, is there a solution for this set of inequalities, you would say, no, there is not, because there's no point at which they overlap. The intersection of these two inequalities is the empty set. Now I could change that, right? If I had a different inequality, what if I changed this? Let's see, I could change it to... What if it looked like this? Well, now I do have an intersection. So this little tiny region where these two pieces intersect, that would be the solution for this system of inequalities. Again, notice that my red line is a dotted line. So wherever that dotted line goes is not part of the solution region. It's only the shaded, the fully shaded parts that overlap or intersect between these two inequalities. Alright, so that's a bit about how to identify whether there is a solution or not when we're looking at graphs of systems of inequalities. When you're doing them by hand or whether you're doing them on a graphing calculator, just be careful. It is so easy to type in the wrong symbol, forget, a sign. So easy to make a simple mistake. So I encourage you to double check, triple check what you're typing in or what you're doing, because it'll save you time in the long run. Alright, so that is a bit about combining inequalities, going back and forth between set notation and inequality notation, and a bit about graphing inequalities. I'll see you guys next time.